Hello everyone, this is eWin's lab. Welcome to the rUDP packet structure demonstration. In this video, we'll explore exactly how data is packaged and transmitted in our reliable UDP protocol. Let's begin. An rUDP packet is like an envelope for sending data over the network. Just like a physical envelope, it has two main parts. First, we have the header. This is always exactly 16 bytes and contains all the metadata about our packet. Think of it as the to and from information on an envelope. Second, we have the data section. This can be anywhere from 0 to 1456 bytes and contains the actual content we want to send. Now, our protocol uses 4 different types of packets. Start packets initiate a connection. End packets terminate a connection. These two types of packets are also called handshake packets. The third is data packets, which carry the actual file content. And finally, ACK packets to confirm receipt of data. Each type serves a specific purpose to establish reliable communication. Let's look at the header structure in detail. The header is divided into 4 fields, exactly 4 bytes each. The first 4 bytes specify the packet type. In this example, we are showing a data packet, which has type value 2. This tells the receiver what kind of packet they are processing. Next, bytes 4 through 7 contains the sequence number. For data packets, this starts at 0 and increment with each packet. This example shows the packet is number 5, meaning it's the 6th packet in the sequence since we start counting from 0. Bytes 8 through 11 specify the data length. This packet contains 1456 bytes. That's the maximum allowed. We'll explain why we use this number later. Finally, byte 12 through 15 contains the CRC32 checksum. This is calculated over the data portion and allows us to detect if any corruption occurred during transmission. It is our data integrity check. And there we have it! Yay! A complete 16-byte header ready to be attached to our data. Okay, as I promised you a couple seconds earlier, here we'll explain why can we only send 1456 bytes of data per packet. The answer lies in network protocol layering. Starting with Ethernet, we have a hardware limitation called MTU. The full term is Maximum Transmission Unit, which is exactly 1,500 bytes. This is the largest frame that can be sent over Ethernet networks. But we need to use some of these bytes for protocol headers. First, the IP protocol header needs 20 bytes for routing information, things like source and destination IP addresses. That leaves us 1480 bytes. Next, legacy UDP needs 8 bytes for port numbers and basic checksums. We are down to 1472 bytes now. And finally, our rUDP protocol needs 16 bytes for the header we just discussed. So the math is 1,500 minus 20 minus 8 minus 16, which equals exactly 1456 bytes available for your data. This means if you need to send a file larger than 1456 bytes, it must be splitted across multiple packets. That is where our sequence number become essential. They can help reassemble the file on the receiving side. Let's examine each packet type in detail. I'll show you actual examples of what these packets look like in the logs. Start packets initiate a connection. Notice the sequence number here is random. In this case, 3928 and so on. This random number helps identify this specific connection. Start packets do not carry any data, so the length is 0, and the checksum is unused. Similarly, end packets terminate the connection. They use the same sequence number as the start packet that opened the connection. This confirms we are closing the correct connection. Again, there's no data payload. Data packets are where the real work happened. They use sequential numbering starting from 0, contain actual file data. Here we see 1456 bytes and include a CRC32 checksum to verify data integrity. Finally, ACK packets provide reliability through acknowledgement. The sequence number in an ACK represents cumulative acknowledgement. In this example, it's just like saying, hey, I've received everything up to packet 5. If the sender does not receive an ACK within the timeout period, then it needs to retransmit. And this combination of packet types enables reliable, ordered data delivery over UDP. Let's walk through a complete example of converting actual data into a packet. We'll start with a simple text file containing Hello World. First, we convert the text into bytes using ASCII encoding. Each character becomes an hexadecimal value. H becomes 48, E becomes 65, and so on. Notice the space is x20. Our 12-character message becomes 12 bytes. Next, we calculate the CRC32 checksum over these 12 bytes. The CRC32 algorithm produces a 4 bytes value. This checksum will allow the receiver to verify that the data hasn't been corrupted. Now we build the complete packet. The header comes first with type fields set to 2 for data. Sequence number 0 since this is our first data packet. Length field set to 12 and our calculated CRC32 checksum. Then we append our 12 bytes of actual data. The result is a complete 28-byte packet, 16 bytes for header plus 12 bytes of data. This packet is now ready to be sent over the network, and that's how your data becomes packets in the rUDP protocol. Here's a table comparing our rUDP with standard protocols. UDP is fast but unreliable. Our rUDP adds acknowledgement and retransmission for reliability. TCP provides full reliability with complex mechanisms. For overhead, UDP uses 8 bytes. rUDP uses 24 bytes in total, and TCP uses 20 to 60 bytes. And this concludes our rUDP packet structure demonstration. Thank you very much for watching.